for the last time ever. I don't think any university profs are bringing that joke out. Pretty sure. There it was. I got something in my eye now. Allergy. Okay. A conducting wire is carrying current towards the top of the page as shown below. So, what can we do with a conducting wire? If they wanted the direction of this wire's magnetic field, I would point my thumb in the direction of the current and my fingers would curl in the direction of the magnetic field. And it's that magnetic field that's interacting with the external one, which is why you get a net force, by the way. I don't know if I mentioned that. Because now it's saying, due to the presence of a magnetic field, the wire is experiencing a magnetic force directed out of the page. What's the direction of the field? So I'm going to use my three-dimensional right-hand motor rule. I have current going up the page. Magnetic force is out of the page. So for me, facing the board, I would hold my hand like that, palm pointing out of the page. I think it was Zach yesterday who came up with actually a good analogy that I'm going to steal for the rest of my teaching. He said, oh, Mr. Dewitt, this is how you remember the Force, because you're doing Star Wars. The Force comes out of the palm like Star Wars, the Force. Zach, I'm going to steal that. I may even give you credit. Might not, because some of my best ideas are stolen, but I might give you credit for that. So, force out of the page, and I guess the magnetic field is which way? Got to be left. So the multiple choice section of your test on Thursday, I think there's 8 questions, and probably 6 of them will be right-hand rule variations. Whether it's the single wire carrying a current, what magnetic field does that create? Whether it's a solenoid that you're holding in your hand, and probably more than one on this, because I can give you, I'll give you the current and the field, what's the force? I'll give you the force and the current, what's the field? I'll give you the force and the field, what's the current? I got lots of options there, I can do that. Okay. Suppose the magnetic field is changed and now the wire experiences a force pushing it to the left. So now I would hold my hand in this manner. You know what? I think into the page, yes? A stream of protons is acted upon by magnetic force while traveling perpendicular, to magnetic, you know what? This is going to be using F equals Q V, B. And all of these need to be perpendicular. Did they say the word perpendicular in this question? Yes. So I'm not going to be worried about that at all. I guess they want me to get the V by itself. V is going to be what? F divided by QB. They gave me a force, 5.8 times 10 to the negative 14. Protons, so 1.6 times 10 to the negative 19. It's a proton. If it's an electron, you don't put the negative into here. You use the negative to figure out direction if they ask you a directional component. And we wouldn't use the negative. We would say, well, an electron moving left, that's a proton moving right. That way we just have a right-hand rule. B is 0.6 Teslas. Pretty big magnetic field. Not crazy big, but yeah, fairly big. I have no idea. 5.8 scientific notation, negative 14 divided by bracket 1.6, scientific notation, negative 19 times 0.6. You get a speed of 6.04 times 10 to the 1, 2, 3, 4, 5, which seems about right. Subatomic particles move pretty fast. In fact, this might even be a bit slow. 6.0416, so 1, 2, 3, 4, 5, 6.04 times 10 to the 5th meters per second. If you got that 2 out of 2, otherwise I would give you a half mark if I saw that. Half mark for getting the V by itself, half mark for the numbers, and a half mark for the answer. Ooh, a wire carrying 5.2 amps as shown in the above diagram. And what's the strength of the magnetic field? So I think I'm going to use for a wire F equals Bill. Now, all of these need to be perpendicular. I looked at the picture. They all are. So we're good here. They want me to get the B field by itself. I guess that means that B is going to be F over IL. It's going to be 2.4 times 10 to the negative 2 divided by 5.2. Am I going to use 8 centimeters or 4 point? Well, so first of all, I'm not going to use centimeters at all. I'll convert. Am I going to use the 8 or the 4.2? What section of the wire is in the magnetic field? What section of the wire is experiencing the force? I'm going to use the 4.2, not the 8. I guarantee there might be a question like that in your future. That's an easy way for me to at least give you, if it's multiple choice, one mistake to pick from. So yeah, not the 8. The whole wire is not experiencing the force. Only that which is inside the magnetic field is experiencing the force. So I'm going to use the 4.2 centimeters or the 0.042 meters. And I'm going to get a magnetic field strength of... Check for typos. I do have a typo. 2.4 times 10 to the negative 2, 5.2 amps, 0.042. I get 0.11 Teslas. Fairly big magnetic field. Not crazy big, but pretty big. If you got that 2 out of 2, otherwise I would give you a half mark for that. Half mark for that, half mark for that, and a half mark for the numbers. If you accidentally used the 8 centimeters, I would give you a 1.5 on this question. What's the direction of the magnetic force? Okay, current going that way, magnetic field into the page, down the page, yes? 1 mark. An electron, it's an electron, so I know the charge, I know the mass. Moving at that, moves perpendicular to a magnetic field. What's the magnitude of the force? So I guess the force, this is going to be straight plug and chug. It's going to be QVB. It's going to be 1.6 times 10 to the negative 19. V, 6.2 times 10 to the 6th. B, 8.5 times 10 to the negative 3. (1.6 times 10 to the negative 19, 6.2 times 10 to the 6th, 8.5 times 10 to the negative 3, and I get 8.432. I'll go 8.43 times 10 to the negative 15 newtons. Is that a big force? For the electron, that's massive. Try dividing by the mass, and you'll see the acceleration this thing is undergoing. It's crazy. If you got that right, 2 out of 2. Otherwise, I guess 1 mark for that, half mark for the numbers, and a half mark for the answer. I like B. This is probably going to be a written question. In fact, I'm going to be really blatant. I think one of your written questions, I'm going to give you, oh, did I give you a solenoid? Yeah, I'm going to give you a solenoid like this. I'll probably have you calculate the magnetic field strength, and then once you have the magnetic field strength, I'll probably give you a charge, and we'll figure out what the radius is. So B says, what's the radius of the circle? What we're going to say is magnetic force is what's pushing me in a circle. QVB equals MV squared over R. One of the V's does cancel. And so we have a Q, a B, an M, a V, and an R. There's 5 variables. Sarah, as far as I'm concerned, I can give you any 4 of those variables and we can find the 5th one. Okay? And I could even make you figure out the magnetic field by giving you the specifications of a solenoid and saying, we're putting this inside a solenoid, that's what's creating the magnetic field. They want the radius, so I guess R is going to be MV over QB. It's going to be M. It's an electron, 9.11 times 10 to the negative 31. V, what was it, 6.2 times 10 to the 6th. Q, it's an electron, 1.6 times 10 to the negative 19. B, 8.5 times 10 to the negative 3. 9.11 times 10 to the negative 31 times 6.2 times 10 to the 6th divided by bracket 1.6 times 10 to the negative 19 times 8.5 times 10 to the negative 3, and I get 0.004 meters. So about 4 millimeters, not a very, very big radius, but detectable. I'm going to write it, I think, in scientific notation, 4.15 times 10 to the negative 3 meters. What's the kinetic energy of the electron? Oh, just good review. Oh, if you got that 2 out of 2, otherwise I would give you a half mark if I saw QVB equals mv squared over r, half mark for getting the r by itself, half mark for the numbers, and a half mark for the answer. What's the kinetic energy? Well, that's going to be a half mv squared, so 0.5, 9.11 times 10 to the negative 31, 6.2 times 10 to the 6th, don't forget the squared, 0.5 times 9.11 times 10 to the negative 31 times 6.2 times 10 to the 6th, don't forget the squared. I get 1.75 times 10 to the negative 17. People nodding? Joules. What is the magnetic field strength inside a solenoid of length 3.2 centimeters? Nice try, Duick. 0.032 meters. Having 600 turns of wire with a current of 4.5 amps. So our magnetic field for a solenoid was equal to mu naught N times I over L. This equation, Zach, has 4 variables. As far as I'm concerned, I can give you any 3. Find the 4th. Here, they're just asking me to find the magnetic field, so it's going to be straight plug and chug. It's going to be 4 pi times 10 to the negative 7. Is that mu naught? I think it is, yes? Okay. N, 600. I, 4.5 amps. L, 0.032. 4 pi, and you've all figured out how to type that number into your calculator without getting a syntax error? I get 1.06 Teslas. Sorry, 0.10. I said 1.06. 0.106 Teslas, I think is what I said. Should have said. Yeah, that's better. I would probably go 1 mark for that. Half mark for the numbers, half mark for the answer. A bar magnet is free to rotate while inside a magnetic field. It's initially positioned kind of slanty. Which way will it point? Well, let's look at the magnetic field lines. Magnetic field lines point from north to south, which means this big external magnet that we don't even see must have had a north pole over here and a south pole over here. And like poles are going to attract, so the north is going to point here, the south is going to point here. The final orientation would definitely be in situation A. And that's the direction a compass would point. Okay. 1 mark. Can you give yourself a score out of 16, please, at the top of the page? Ultimate magnetic forces review. We're going to do some pretty strong crossing out of some questions and keeping some questions. Or did I do that already? I did that already. Never mind. Okay? I didn't do that already? Some people are saying I didn't. Did I go through the ultimate forces?
We did.
We did. Okay. Then we're good. I told you which questions I like. So then, if you want to get up the notes from last day where we paused. This is not going to be on your test. This is just for cool nerdishness. And it's also going to have lots of right-hand rule practice. So this is me coming up with an interesting way to review the right-hand rule. You're here? So we were starting to learn that by dragging a metal bar through a magnetic field, as long as the bar was perpendicular to the direction of motion, we could separate charges. You would actually feel a force resisting you. How many of you have ever used one of these rechargeable flashlights where you have to turn a crank in order to recharge it? When you use this, you actually feel some resistance. It's not because this is poorly oiled or anything like that. There's very little friction in here. What you're feeling is the force required to separate those charges. You're actually feeling it. Now, this is moving it in a circle, which we might not get to, as opposed to just pulling a straight bar. But if you're ever cranking a rechargeable object, that force you're feeling is that resistive force. You're feeling QVB or build, depending on whether you're moving a wire or a single charge. In this case, you're moving a wire. So what if we connect the moving strip to conducting rails? Then the strip will act like a battery, and we'll get current flow. So we're going to take that piece of metal, and we're going to lay it down on more metal, on metal railings. Example 6 says, show that the polarity of the moving wire is like the cell to the right. So show that we're going to get a battery with current pointing downwards. So again, what I told you is I always just put a single proton in the middle. That's all the metal that's all the charges sitting in there, but I just stick one in the middle. Which way is that proton moving? Which way is the bar moving? I'm looking for where that starts with the letter R. So the protons are all moving to the right, so we'll point our thumbs to the right. And then I couldn't get the graphics to work. It says the region of the field is out of the page. So the magnetic field is going to be which way? Out of the page. So I'm going to point my fingers like this, I guess. Which way will the charges feel a force? Yeah, this is correct. We will feel positive charges moving this way. Then once they get to the wire, they're going to keep going. In fact, this resistor would light up if it was a bulb while you were pulling it. This is equivalent to having a battery inside a circuit, a voltage source, an EMF. Now, if there is current flow flowing through the moving wire, then there's also going to be a magnetic force that slows things down. So as soon as you start to move it, not only are the positive charges moving to the right, but they're also moving down. See them, see them, see them? So point your thumbs down the page now. Magnetic field is still out of the page. Which way are your palms pointing? To the... You're going to feel a force resisting you. It's the same force that you feel resisting you when you try cranking a rechargeable flashlight or radio or whatever you're doing. This is rotational as opposed to, come on in, just get going. We're continuing from where we left off. This is a linear force as opposed to rotational. But you would feel this weird force tugging against you. So, the magnetic force would be in that direction. This is important. If that wasn't there, Mud, you would get free energy. You would get current, and you wouldn't lose anything doing it. This is the universe stepping in and saying, no, you don't get anything for free. Otherwise, you could grease this down, put it on a very, very slight incline, and just have it slide down the hill with gravity, and hey, free current. Okay. Example 8 says this. The strip below is 1.2 centimeter, or 12 centimeters long, moving at 4.7 meters per second. The external magnetic field is that. It wants you to figure out the induced voltage and the induced current. I'm going to skip all that. I'm going to skip the numbers because we're just doing right-hand rule review. So we would say, first of all, there's our positive charge. As we just start to move this bar, which way are the positive charges moving? To the right. Which way is the magnetic field? Out of the page. So I point my thumb to the right, fingers out of the page. This will induce a current, clockwise in this case. But as soon as the current kicks in, now charges are also moving down the page. Magnetic field out of the page. Now we would feel a force to the left. And that force to the left would be Bil, B-I-L. Which the current you get from the voltage and the resistance. Sarah, people looked at this and then they said, hey, how can we improve on this? So one question they asked is, what if instead of a single bar, what if we move a loop of wire through a magnetic field? What will that do? Well, I'm going to, instead of moving a loop of wire, I'm going to treat this like 4 separate wires. Put a little positive right there, a little positive right there, a little positive right there, a little positive right there. That top section of wire, which way is it moving? To the, looking for where it starts, letter R. So point your thumbs to the right. What direction is the magnetic field? Out of the page. In that top thin section, charges, don't write this down, are technically getting forced down, but is there anywhere for them to go in that thin wire? This is that same situation we talked about yesterday. The top and the bottom are moving parallel to the direction of motion. You're not going to induce much charge. You're not going to do much separation of charge. So the top and bottom essentially do nothing. What about this front section of wire? Which way is it moving? To the? Looking for the front section of wire. Which way is it moving? To the? Looking for where it starts letter R? Right? And it's perpendicular to motion. So, you know what? Charges are going to flow from that front wire in that direction. Yes? What about the back section of wire? Which way is it moving? Also to the? Which way are charges going to flow here in that direction? And what you end up with are 2 opposing currents that cancel each other out. Doesn't work. Rats. Okay? So scientists, physicists thought about it for a while and, okay, what else can you do? What if instead of getting a current, what if we supply a current? So here we have our metal strip, but right now it's at rest. We have an external current source. This is going to be a rail gun. So let's follow it. Here's our battery, George. Which way are charges leaving from this battery, upwards or downwards? So let's draw in the current. The current will be going this way. Inside the beam, it's going upwards. Which way are charges moving inside the beam? Everybody point your right thumbs upwards. What direction is the magnetic field? Still out of the page. So upwards, magnetic field out of the page. If I hold my hand this way, ooh, now the bar is going to feel a force not to the left, but to the, we're going to get a force to the right. It's going to accelerate. As it speeds up, remember, there's a proton sitting right there. It starts to accelerate. So now the proton is moving in this direction because it just started to accelerate. Which way is the magnetic field still? Which way is the magnetic field still? Which way is the magnetic field still? Out of the page. So if I point my thumb out of the page, which way are the protons feeling a force now? Down the beam. The battery is pushing charges upwards in the beam, but as soon as it starts to move, they feel a force down the beam. The maximum speed this railgun can achieve is when those 2 currents are equal. It will speed up, speed up, speed up until we hit just the right V so that the QVB, the bill going down, is canceling out the current going up. That's how a railgun works. So as it speeds up, the induced voltage increases, the current in the bar resisting the source current increases, and you reach an equilibrium point. But this is how a railgun works. Okay? So some applications, and then we're going to finish with this. We've thought this could be a method of launching vehicles from space stations without needing to turn on your rockets. You probably don't want to fire your rockets if you're half a meter from the International Space Station, if you're docked with the International Space Station. So one way of doing it would be having the spaceship itself act like the conducting bar. So you would just have a strip of metal running like this. You would have magnets, let's say, going into the page, a magnetic field, a couple of big solenoids that are run from solar power from the sun. And you would have a big battery also being run from solar power from the sun. So let's draw in the current. Current goes this way, this way. It would go down through the spaceship like that. So Mud, which way is the current moving inside the spaceship? No, which way is the current moving inside the spaceship? I'm looking for where it starts, letter D. Down. Everybody point your right thumbs down. Which way is the magnetic field? What do those X's mean? So which way will this spaceship feel a force? To the right. And it will very, very gently, with no rockets required, get a nice little push off of the launch. So that's one possible application that we could do. The other application is in electric motors. Now, electric motors, instead of a single bar, you have a spinning coil of wires called an armature. And so it's a little bit trickier when you have something spinning. But basically, for an electric motor, as soon as you start to spin it, it starts to create a back voltage resisting the source voltage. And the fastest the motor can go, if you ever use, for example, an electric drill, and you just hold the trigger down under no load, it'll reach a maximum speed. That maximum speed is when the induced current from the spinning motor exactly canceled out the source current from the plug or from the battery. You get what we call a back EMF, a back voltage. It's why electric motors are so nice, because at maximum speed, what causes heat in electric devices is current, because those are moving charges running through the circuit. They're running into other charges, and they're generating heat just the same way when you rub your hands together. But what's nice about electric motors, Zach, is when they're at maximum speed, the back voltage, the back EMF causing a current, and the source current are nearly equal and cancel themselves out almost. And so electric motors run at their coolest, at their most efficient, when they're running at their maximum. Other motors don't do that. Gasoline motors, very different. The more you rev them, the more heat you waste. Electric motors, nuh-uh. It's one of the many reasons why electric cars are way more efficient. So how do you make a railgun? Put your pencils down, look up. You can try this yourself at home.
Railguns are simple devices that can accelerate a projectile to very high speeds. The Navy railgun has the record, accelerating a projectile at a speed of Mach 7 or more than 5,000 miles per hour. A simple railgun can be made with just two speaker magnets, a couple of conducting wires, a 12-volt battery, a resistor of 0.5 ohms, and an object that is a conductor, but that is also non-magnetic. When we connect the battery to the wires, the electricity will flow to the first wire, then will go through the projectile, and then will go back to the battery through the second wire. As we can see, the projectile is in contact with the rails. When the current flows, a magnetic field is generated. We use magnets to increase the field. The interaction of the magnetic field and the current generates a force in the projectile. This is known as the Lorentz force, and its direction depends on the directions of the magnetic field and the current. Now, let's power our railgun. If we invert the polarity of the battery, the Lorentz force will change direction and will push the projectile to the right.
So very simple railgun there.
Invert the polarity again.
So what if you crank that up? What if you have a several $million budget? Well, you can get something like this. Which one is it? Electromagnetic railgun. E. It's traveling with some pretty serious speed and kinetic energy. The wall things, that's part of the experiment. How many will it go through? I don't know. I can't remember where I found this, but it was a nice example. And you can get some pretty crazy speeds. So, railguns, and spaceship launchers. Some nice applications. I would love to go on more rants, but I also want to give you time to study and work on stuff. There's no homework attached to this lesson. The rest of this class is yours to work on the ultimate review, to ask me questions, to work on magnetic forces homework. Ladies and gentlemen, that almost brings the course to a close. However, on Tuesday, a week from today, really encourage you, show up. I will be doing something that I think you'll remember for the rest of your lives. It's going to be pretty cool.